Okay, we're in chapter 6.5 now, properties of logarithms. The essential question here says, how can you use properties of exponents to derive properties of logarithms? So we're going to let x equal the log base b of m and let y equal the log base b of n. The corresponding exponential forms of these two equations are b to the x equals m and b to the y equals n. We did that in prior sections. What you will learn in this chapter section is how to use the properties of logarithms to evaluate logarithms, use the properties of logarithms to expand or condense logarithmic expressions, and you're going to use the change of base formula to evaluate logarithms. Okay, so all these things should be very new to you, so let's take a look. Okay, so before we get into doing any examples, we have to go over some core concepts. So the properties of logarithms. So if we're going to let b, m, and n be positive real numbers, okay, we're not dealing with negatives, we're not dealing with imaginaries, and we can't let b be 1 because a base 1, yeah. So anyway, product property. The log base b of m times n equals the log base b of m plus log base b of n. So when we have multiplication here, we add. Okay, it's kind of the same as power rules. Quotient property says if we take the log base b of a fraction, then we take the log base b of the numerator minus the log base b of the denominator. So when we divide, we subtract. And if we have log base b of m to the power of n, this little n here will go out in front, and it's n times the log base b of m. So this rule here you'll use in future courses and when you take derivatives in calculus, for example. So this is the beginnings of some higher maths here, trying to figure out what properties we use for logarithms. Okay, so let's take a look at some examples. Okay, so example 1, using properties of logarithms. So I brought the properties over. They're a little cheat sheet since this is new. And we're going to use the log base 2 of 3 to be an approximation of 1.585 and log base 2 of 7 to be an approximation of 2.807 to evaluate each logarithm. But before I do that, I'm going to put those in the calculator. So I want to find out what the log base 2 of 3 is. To put that in your calculator, you take the log of the 3 divided by the log of your base. So I'm going to do log 3 divided by log of my base 2. And that equals 1.58496, and that's where that 1.585 comes from. They rounded to 3 decimal places. Now, if I do the same here, it's just log 7 divided by log 2. So the log of 7 divided by the log of 2 is how you put this in your calculator, and that's how they get the 2.807, and the next number is a 3. So the 1000th position is less than 5. So that's 7. It gets truncated. So it's 2.807. Okay, so that's just where that comes from. And we're going to use those values to do these. So A says the log base 2 of 3 over 7. So I write the log of base 2 of 3 over 7 equals. And then I look over here and I see that it is the quotient property. And that's going to equal the log base 2 in this case of our numerator. So I'm going to write the log base 2 of 3 minus the log base b, or in this case 2, log base 2 of n, which is our denominator, or log base 2 of 7. And that's why they gave us these values here. So now what I'm going to do is substitute, and I'm going to use an approximation now. So this is exact still, but then when I put a decimal in, it's going to become an approximation. And log base 2 of 3 is 1.585 rounded, minus the log base 2 of 7 is 2.807. So that's going to be another approximation. So 15 minus 7 is 8. This is now a 7. 7 minus 0 is 7. 15, so I have to borrow here from the 1. And 5 minus 8 is 15 minus 8 is 7. And then I get -2. Now let me just check that. You have to be really careful when subtracting. So if I do 1.585 minus 2.807, that's probably not right, is it? No. So the rule when you're subtracting, I just realized what I was doing here. When you subtract two numbers, you subtract their absolute values and take the sign of the smaller. So if you're subtracting a bigger number from a smaller number, so I should have this 1.585 minus 2.807. If I did this without a calculator, I'd take 2.807, and that's the minus, that's the smaller, that's the bigger number, and it's negative. So my answer is going to be negative, but I'm going to subtract 1.585 from that. So 8 reduces or cancels to 7 when I borrow 10. 10 will become a 9, or no, leave that 10. 7 minus 5 is 2. This is a 10 minus 8 is 2. 7 minus 5 is 2. 2 minus 1 is 1. The bigger number is a negative, so my answer is negative 2.222. Okay? Negative 1.222. And when I look at the calculator over here, that's what it is, negative 1.222. Okay? But there's a quick review of, is that math 7 or maybe even math 6? I think math 6, we did that. Okay, so anyway, the answer is negative 1.222 approximately. All right, let me just switch colors here because I'm going to run out of room. So now I will do B right here, and it's the log base 2 of 21. Well, what is 21 with respect of 7 and 3? Well, log base 2 of 21, the log base 2 of 21 equals the log base 2 of 3 times 7, isn't it? Isn't 21 3 times 7? And these are the values they gave us. So that's what you have to do. You have to look up here. And if these are factors of 21, then we can use them as the product. So now we're working with the log base 2 of 3 over 7. So I'm going to move this down here. Oh, it's all 1. Let me just slide this over like this then. So we have the log base 2 of 3 times 7. Well, that is right here. And what we do is we take the log base b of the first number plus log base b of the second. So this is going to become log base 2 of 3 plus log base 2 of 7. And I have an approximation for both. Log base 2 of 3 is 1.585. And log base 2 of 7 is 2.807. So 7 plus 5 is 12, carry the 1. 0 plus 1 is 1, plus 8 is 9. 8 plus 5 is 13, carry the 1. 2, 3, 4. So it's approximately, I should be using approximations at this step and the next one. So this should be an approximation. And this is an approximation. So I get 4.392. Okay, and then finally, the last one, part C, the log base 2 of 49 equals, well, if I look up here, it's not anything to do with 3. It's going to be 7 squared, 7 squared. Or I could do this, the log base 2 of 7 times 7. I'm going to do it both ways here, but they wanted us to do one of each. So they wanted us to do the power property here, but I'll show you that they both work. So if I'm taking the log base 2 of 49, it doesn't equal 7 halves. It equals the log base 2 of 7 squared, not just 7 squared. So the 49 just got changed to 7 squared. And the rule says take the power and bring it out in front. So that's going to equal 2 times log base 2 of 7, which is 2 times, and I don't want an equal sign, I'm approximating with a decimal. So let's do that. And the log base 2 of 7 is 2.807. And then when I multiply that, 2 times 7 is 14, carry the 1. 2 times 0 is 0, plus 1 is 1. 2 times 8 is 16, carry the 1. 2 times 2 is 4, plus 1 is 5. I get approximately 5.614. Now, if I did log base 2 of 7 times 7 instead, I would get this to equal the log base 2 of 7 plus log base 2 of 7. And that's going to be approximately log base 2 of 7 is 2.807 plus 2.807. 7 plus 7 is 14. 8 plus 8 is 16. Carry the 1. 2 plus 2 is 4. Plus 1 is 5. And I get, again, 5.614. So these answers are the same, but they wanted us to do it with a power, so that we use this rule here. Okay, so there is the quotient rule, the product rule, and the power rule. Okay, so now you should be able to do problem numbers 3 and 4 in your exercises. Okay, example 2 is expanding a logarithmic expression. So in this case, we are doing what's called expanding. All right, so what does that mean? Well, if we have expand the natural log of 5x to the 7th over y, these rules here apply to logarithms and natural logs. The only difference between the natural log and the log is the base. A logarithm with a base of a real number, such as 2 or 3, or a common log of 10, and natural log is just base e. Okay, so expand natural log of 5x to the 7th over y. Well, the first thing I want to address is the fraction. So I'm going to write the natural log of 5x to the 7th. So this expression is equivalent to the natural log of the numerator minus the natural log of the denominator. That's step 1. Okay, that's the quotient property. So check. And now this is all done. The natural log of y is just simply that. It's a natural log of y. There's nothing to do here, but in this one, we have an exponent and we have multiplication. So the next thing I want to do is the product property. I want to split that up. So that's going to be equivalent to the natural log of 5 plus the natural log of x to the 7th. And then I'm bringing down the natural log of y. That didn't change. But the natural log of 5x to the 7th is the natural log of 5 plus the natural log of 7. Okay, and we're still not done. We then have to take the natural log of 5. That's done. But I need to do the power rule here. Okay, so I have the natural log of x to the 7th. My n in this case is 7. That gets moved out in front. So this is going to become plus, the 7 goes out in front. So that's going to become 7 natural log of x. And then this minus natural log of y just comes for the ride. So notice what happened. Step 1, we subtracted because we had division. Then we moved that 5 away from the natural log of x to the 7th by the product property. And then the natural log of 5 comes down, and this power goes out in front. That's the power property. And so this is equivalent to this in expanded form. Now, without knowing what x and y are and having two unknowns, this is as far as we can take this at this time. Okay, so just like expanding, we can also condense logarithmic expressions, and that's what we're going to do in this example. So we have the log base 9 plus 3 log base, actually log base 10. It's a common log. So let's start over. The log of 9 plus 3 times the log of 2 minus the log of 3. So when we're doing these, by the way, I haven't mentioned this yet, your bases have to be the same. This is base 10. This is base 10. This is base 10. When there's nothing there, it's base 10. Okay, so your b's have to be equal in order to do this. And now we have a plus right here, and we have a minus right here. So we know that when there's an addition sign, we're going to multiply right here. And when there's a minus sign, we're going to divide. And then we have a number in front. So we also have an n right here, and that's going to become the power. Okay, so that's what we're going to start with. So I'm going to say that this equals the log of 9 plus, I'm going to take this 3 and move it up to the power. So that's going to be the log of 2 cubed minus the log of 3. Okay, so I wanted to show my work there. And then I can simplify this. So I'm going to do it in 2 steps. I'm going to leave this. I'm going to say the log of 9 plus the log, and 2 cubed is 2 times 2 times 2, which is 8, minus log 3. Now with the addition, that becomes multiplication. So that's going to become the log of 9 times 8. I'm going to show all my work because I'm new at this. Okay, well, not really, but you are. And the log of 9 times 8 is the log of 72 minus the log of 3. And then finally, I'm going to do the quotient property at the end. And this is going to become the log of 72 divided by 3. Okay, and that can be simplified. 3 goes into 7, so it's going to be the log of 3 goes into 7 twice, with a remainder of 1, and 3 goes into 12 4 times. So this simplified down to the log of 24. Okay, and I'm going to just for kicks show you that in the calculator. So where'd my calculator go? There it is. So if I clear this and I go log 24, enter, I got 1.380. So this up here should be equal. So we have the log of 9 plus, oops, I clicked, but it missed. The log of 9 plus 3 log 2, close parentheses, minus the log of 3, close parentheses, and hit enter. So notice the log of 24 is equal to our original. That's how you can use a calculator to check to see if you condense correctly. Get the same decimal, you did it right. Okay, so now you should be able to do problems numbers 23, 24, and 30. Okay, core concept again. Another core concept, the change of base. I kind of mentioned it already in this lesson when I got the calculator out. But it says if A, B, and C are positive real numbers with B not equal to 1, the base, in other words, and C not equal to 1. So if C were 1, that'd be the log base B of C, or the log of C 0, and the log of 1 is 0, so you can't divide by 0. So that's why you can't have C to be 1. Okay, so what we're doing is we're changing to the same base. The log base C of A equals the log base B of A divided by the log base B of C. And the B usually we make 10. We usually make it a common log. But in particular, the log base C of A is the log of A divided by the log of your base. And the log of A, if you have the log base C of A, you can also change it to a natural log of A over the natural log of the base C. Okay. So it's easier to explain with an example, so let's do it. Okay, changing a base using common logarithms. Evaluate the log base 3 of 8 using common logarithms. So remember, the log base 3 of 8 equals the log, and it is base 10 if you just say the log of what you're taking. The log base 3 of 8 becomes the log base 10 of 8. In this case, I'll write the 10, but you don't need to, divided by the log base 10 of 3. So what we're going to do is take the log of the, I say log of the big number. And when I say big number, I mean font size, not number size, because this could be base 8 and this could be a 3. The log of the big number is this number divided by the log of the little number, which is the base. So log of 8 divided by log 3. And I just put the tens in there because it's a common log. You don't need a 10, but I just put it there. That's the same as this. The log of 8 divided by the log of 3. And that's going to approximate when you put in your calculator. So you just simply go log 8 parentheses divide log 3 parentheses, enter, and I got 1.89. It's 27, so I'm just going to go out 3 decimal places to 1.893. Okay, and that's how you do it. It's really simple. Log of this divided by log of that. Now you should be able to do problem numbers 33 and 34. Okay, so this says changing a base using natural logs. So this is really no different than what I just did, except instead of a base 10 or a common log, we're going to use base e, which is a natural log. So I'm going to write the log base 6 of 24 is going to equal, and we're using natural logs, that's going to equal the natural log of 24, log of the big, or natural log of the big, divided by the natural log of the base or the little. So it's just simply ln of 24 divided by ln 6. So then we use the ln button here. ln 24 divided by ln 6. And I hit enter, and I get an approximation of 1.7737. 7 makes the 3 a 4. So 1.774. Okay. And that's it. That's how you do change of base using logs and natural logs. Now you should be able to do problem numbers 39 and 40 in your exercises. Okay, example 6 is solving a real life problem. So for a sound with intensity I, hello. Okay, for a sound with intensity I, which is watts per square meter, the loudness L sub I, or L of I mean, of the sound is in decibels, is given by this function. So L of I is 10 times the log of I divided by I sub 0, which we say I naught, where I naught is the intensity of a barely audible sound, which is approximately 10 to the negative 12 watts per square meter. So let's just pause right there a second and remember what they mean by 10 to the negative 12. So if I have 10, the decimal's here. Negative 12 means to move the decimal 12 places to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then erase the decimal that was there, and I don't need that 0. So that's 10th, 100,000, 10,000, 100,000, million, 10 million, 100 million, billion, 10 billion, 100 bill of a billionth, 1/100 billionth. Okay, so it's a really, really small number, really, really close to 0, therefore barely audible. Anyhow, there's that. It's always a good idea to figure out what they're talking about and understand everything. So an artist in a recording studio turns up the volume of a track so that the intensity of the sound doubles. Okay, the sound doubles. By how many decibels does the loudness increase? So the question is, how many decibels did the loudness increase? So we're going to address this as saying, well, if this is L of I, let's just call that the original volume. Let I be the original intensity, and we're doubling the intensity so that the intensity of the sound doubles. So we're going to let I, capital I, be the original intensity. Okay, so if I is the original intensity, 2I is the result of turning it up. Okay, so they turned the volume up so the sound doubles. So I became 2I, that's double. So we need to write a formula. The increase in loudness, so you'd write the increase, which is what we're trying to find. The increase in loudness equals, and it's going to be the 2I, what we increased it to, minus the initial volume or loudness, and that will equal the intensity increase, the decibel increase. So that's going to equal the loudness. Actually, it's loudness function. I forgot that. So right here, L of I. So we're going to take L of 2I minus L of I. That's what we're going to do. The initial, and we're going to subtract that from the loudness of double that initial. Okay. So how do we do that? Here's our base 10. And here's our equation that they gave us. Okay. So the equation is 10 times the log of I over I naught. So we're going to replace those with, that is now going to equal, so L of 2I is going to be 10 times the log of 2I divided by I naught minus 10 log. I'm going to put a dot here too, so it doesn't look like log. 10 times the log of 2I over I naught minus 10 log I over I naught. Okay, that's how we begin. And as you can see, we have 10 in both, so we can factor that out. So it's going to be 10 times the log of 2I divided by I sub 0 or naught minus log I divided by I naught. Okay, so we got that 10 out of there. Next thing we want to do is do our rules. So it's 2, think of this as 2 times I over I naught. So I'm going to erase this and show you, instead of writing it up here in the numerator, it might be a little confusing if I just do the next step without taking that out first. You can have a 2 in the numerator, or you can have the 2 out in front, multiplying 2 times I over I naught. And now I have a multiplication problem. And so that's addition. Now I can break that up with our product property. So that's going to be the log of 2 plus the log of I divided by I sub 0 or I naught, and then minus the log of I divided by I naught. Okay, so I just did a product rule because there was multiplication here, and we switched it to log of 2 plus log of I naught. I got that 2 out of there. So look what's going to happen here. I have the log of I over I naught minus the log of I over I naught. Anything minus itself is 0. And that's going to simplify to 10 times the log of 2. And this is all gone. Okay. So the loudness increased by 10 log 2 decibels. Well, what is that? Turn my calculator on. And if I put 10 times the log of 2, then that becomes approximately 3.010. Okay, so how many decibels did the loudness increase? Approximately 3 decibels. All right, so that's how you use logarithms in a real world situation. And now you should be able to do problem number 43 in your exercise. Okay, so this brings us to the end of chapter 6.5. Hopefully you don't find logs or natural logs that daunting. So you should be able to do these problems in the exercises. Thanks for watching and have a great day.